So, in the last lecture we finished the proof of theorem about cyclotomic fields, where we computed rings of integers as well as torsion subgroup of cyclotomic fields, which are of the form q zeta p to the r for a prime number p and r is a natural number. And I promised you a theorem that I was going to prove later on, which was that so let me write it down as a proposition now. So, let n be p1 to the r1 all the way up to ps to the rs, where pi's are distinct prime numbers. Then q pi to the ri sorry, not this way, the notation is different for us. So, zeta pi to the ri intersected with q zeta p j to the rj is equal to q if I is not equal to j, right. So, if pi is not the same as to the prime pj, then you get this, and hence q zeta n, this is compositum of q zeta p1 to the r1 and so on up to q zeta pr to the ps to the rs, and Galois group of q zeta n over q is isomorphic to z mod nz cross, okay, and which in turn is isomorphic to product I going from 1 to s z mod p to the I to the r I z cross. Okay. Further, the primes that ramify, so further p1 up to ps sorry, are the only primes that ramify in q zeta n, okay, and the ring of integers of q zeta n, this is z zeta n, okay. So, so that is all I am going to say. I am not going to compute the discriminant of this field, because that is a somewhat involved computation, and we are not going to do it in this course. So, let me just the only thing that perhaps need an explanation is the last part, okay. Let me say how does one do the first parts. So, okay, let me do it one by one. So, q zeta p to the I to the ri intersected with q zeta pj rj. If this field is k, then pi is unramified in k. Yeah, pi is unramified in k, and pj is also unramified in k, because pi is unramified in the second field and pj is unramified in the first field. Hence, k over q is unramified at all primes. Hence, k is equal to q, because the only unramified only extension of q that is unramified everywhere is q itself. right. And then we know that Galois group of the compositum q zeta pi r I over q, this is isomorphic to product of Galois group of q zeta pi to the r I over q, and each of those is isomorphic to z mod pi to the r I z cross, and this thing by Chinese remainder theorem is isomorphic to z mod nz cross. Okay. All right. So, the last part says that, so let O be equal to O q zeta n, the ring of integers. We know that z zeta n is contained in O, and we want to show an equality here, right. So, we want that z zeta n is equal to O, right. That is what the claim is, and so we have proven this already for right. So, we have already proven this for the ring of, so for n a power of p. So, already proven when n is p to the r for some prime p, right. So, let us take a example. So, when n is p times q, p not equal to q, prime numbers. So, this is just to get an idea of what is to be done, and maybe I will leave the general case as an exercise for you to do. So, what do we have? We have q zeta p, and then q zeta q, and then q zeta n, which is the compositum of these two fields, right. Okay. So, right. So, the only primes that ramify in q zeta n. So, first of all, let me call this k. So, discriminant of k is some p to the a times q to the b, right, for some integers for some a b in z, right. So, this means that the only denominator that and if you compute, if you compute this thing zeta phi n minus 1, this is a power of up to sign, this is a power of n, right. So, what this means is that if alpha is in O, then alpha can be written as alpha equals summation j going from 0 to phi n minus 1 a j zeta n to the power j, where a j are rational numbers with only p and q in the denominator. Okay. So, what do I conclude from this? Well, not much at the moment, because I also want to know whether, I mean, I do not want these things in the denominator either, right. Right. Okay. So, the idea is to look at the trace of this in various subfields and then conclude that yeah, then conclude that yeah. So, the idea is to consider trace from k to q zeta p of alpha and trace from k to q zeta q of alpha, right. And then we know that so that will give you some bound on what the denominators can be, and you work it that way. So, I will leave this as an exercise, the rest of it. I had not planned to do this. So, finish the proof. It is not a easy exercise, but it sort of tells you how to break up a study of q zeta n into q zeta into its prime powers. Okay. All right. So, what I had planned to do today is computations of class numbers. So, computation of ideal class groups. So, this is what we will do over the next few lectures, 2 or 3 lectures, and we will look at lots of examples of computations of class group. Okay. So, recall Minkowski bound. What does this say? This says that if k is a number field, so this is a number field and R1 is equal to number of real places, R2 is equal to number of complex places, right. dk, this is discriminant of k, then Minkowski bound and n is the degree of the number field, right. This is R1 plus 2 times R2, right. Then Minkowski bound, remember, is the following. Minkowski bound is n factorial by n to the power n 4 by pi to the R2 and square root of mod of the discriminant. Okay. So, you take the positive square root of mod of the discriminant of that number field. Okay. And what did we proved the following theorem a long time ago. We proved that any ideal class in the class group of K contains an integral ideal A such that norm of A is less than or equal to, so norm of A is a natural number, is less than or equal to Minkowski bound. Okay. All right. So, how do we use this to, so we use this to compute ideal class group. Of K. So, what is the roughly the steps involved? So, the steps are the following. Okay. So, first is we compute Minkowski bound. So, you do an explicit computation and you get some upper bound for the Minkowski bound, which is close enough. Then factorize all primes in Q less than or equal to Minkowski bound. And the last one I am going to be somewhat fuzzy, which says that you find which of and find all the relations between these prime. Yeah, so factorize all primes in Q in the field K, right. So all primes P such that P is less than or equal to Minkowski bound, and you find the prime factorization. So, P OK, this is some, this will be some P1 to the E1 up to PR to the ER, right. And so, all these PIs, they generate the ideal class group, the group CLK, and so we want to find out what the order of each of these is. So, are some of them trivial or whatever, right. So, this is roughly the algorithm, this is roughly how you do it. So, let us look at some examples. Okay. And I will do it somewhat more systematically in the next lecture, but now let us just do this. Right. This was one of our examples where I said unique factorization does not hold, right. So, what is the ring of integers of this? So, -5 is congruent to 3 mod 4, right, and so the ring of integers is z square root of -5, right, and the discriminant is -20. So, the Minkowski bound right, what is R2? R2 is 1, R1 is 0. So, Minkowski bound is and n is of course 2. So, 2 factorial by 2 to the power 2 into 4 by pi into square root of 20, right, and so you get 2 by pi into square root of 20. Right. So, if instead of pi I put something like 3, and if instead of square root of 20 I put something like 5, yeah, then I get 10 by 3, which is less than certainly less than 4, right. And so, this may be a bit of an overkill, but I am doing the, I mean this may not be the best possible bound, you may even be able to get it less than 3, but this is enough for us. So, what I am going to do is I am going to factorize. So, find 2 OK and 3 OK, right. So, 2 OK, so what is the right, you want to find out what this factorizes as modulo 2, and so this is congruent to x square minus 1 mod 2, which is same as x minus 1 square mod 2, and x square minus 5 is congruent to x square minus 2 mod 3, and this is irreducible mod 3. So, this means that 3 OK is a prime ideal in K, right, whereas 2 times OK, this thing factorizes as right, this thing factorizes as P2 squared, right. So, 2 is ramified, and I mean this we need not even have computed this thing, right. We know that it divides discriminant, so it is ramified. Okay. So, CL of K is generated by P2, and we know that and P2 square is principal, right. So, hence CL of k is either trivial or CL of k is isomorphic to Z modulo 2Z. So, which one it is? Which one is it? Right? We want to know which one is it. So, CL of k is trivial if and only if P2 is principal. Right. So, this is if and only if P2 is equal to alpha for some alpha in OK. Right. But if this holds, so this is if and only if there exists alpha in OK such that norm of alpha is equal to plus or minus 2. Right. But if alpha is a plus square root of minus 5 times b, then norm of alpha is a square plus 5 b square. So, I want this to be plus or minus 2 and this has no solutions. This has no solutions, right. Hence, P2 is not principal. Hence, the ideal class group of K is isomorphic to Z mod 2Z, right, and it is generated by the prime above 2. Right. So, okay, we will look at lots of such examples, but before going there, let's do the following. So, are there? So, let us take the case K is a real quadratic field, right. So, n is equal to 2, R1 is equal to 2, R2 is equal to 0. So, then the Minkowski bound is equal to 2 factorial by 2 square times square root of discriminant of k, right. So, I want to know when this is less than 2, right. So, I want to know, so this is less than 2 if and only if 2 factorial by 2 square root of dk will be positive. So, I will stop writing that, and so this means that square root of dk is less than 4, right, which means that dk is less than 16, right. And so, how many such fundamental discriminants are there, right. So, what are all the possible discriminants? So, this is, so dk is always 1 or 0 or 1 mod 4, right. And so, yeah, and so it can't be 4, right. So, the first possibility is 1, and so the only, so dk is 1 if and only if k is equal to q. So, that is not a real quadratic field. dk is equal to 4 if and only if again right, somehow it is kind of k is equal, I mean this is not possible in some sense, right. It is this is not possible. So, the first thing that is kind of possible is dk is equal to 5, in which case you get k is equal to q square root of 5, right. dk is equal to 8, in which case you get q square root of 2, right. And then dk is equal to 9 is again not possible because it is a square, right. So, the next thing that is possible is dk is equal to 12, in which case you get k is equal to q square root of 3, and then the next possible thing is dk is 13, in which case you get k equal to q square root of 13, and then 16 is sort of beyond bounds, right. So, this means that right, this means that in these cases, so so when Minkowski bound is less than so when Minkowski bound is less than 2, we don't need to check any factorization, we don't need to check any factorization, right. We can directly conclude that ideal class group of K is trivial. Okay. Right. So, this means that CL of K is trivial for K is equal to Q square root of 5, Q square root of 2, Q square root of 3 and Q square root of 13. Of course, that does not mean that these are the only real quadratic fields for which the class number is 1. In fact, there is a very famous conjecture and I think this goes back to Gauss. So, it has been open for a long time, 200 years or more, is that there are infinitely many real quadratic fields K such that class group of K is trivial. Okay. So, we have absolutely no idea how to prove this yet. There is no there are, we do not even know that there are infinitely many number fields with class number 1, let alone real quadratic fields with class number 1. Okay, so, what we did today was compute class group in a particular example and then look at all real quadratic fields with Minkowski bound less than 2. So, we will do similar thing next time with imaginary quadratic fields, and then we will look at lots of examples of computations of class group. Thank you.